Amylase is an enzyme that is produced by the human body. As food is ingested, the process of digestion is started. Food needs to be broken down in order for the body to be able to utilize it as energy. However, chewing and churning food can only do so much. The human body produces specialized enzymes such as amylase that break down different types of food. Amylase breaks down carbohydrates into smaller molecules. It is produced in the mouth by the salivary glands and in the pancreas. Carbohydrates begin the process of digestion as polysaccharides, which are simply large starch molecules made up of multiple smaller sized glucose molecules. The amylase in your saliva breaks down these polysaccharides into maltose, a disaccharide made out of two glucose molecules. As the starch molecules pass through the esophagus and stomach, the amylase from the saliva continues to break down the polysaccharides. Amylase is produced in the pancreas and is released into the duodenum, the upper part of the small intestine, where the remaining disaccharides and polysaccharides are broken down into monosaccharides. Monosaccharides are simply one molecule of glucose and is used as energy for the body. This process of breaking down starch is known as starch saccharification. However, this process is very useful outside of the body as well. All plants consist of starches to some extent. If the chemical links between the glucose molecules that constitute starch are broken, maltose and glucose can be obtained and utilized for different purposes. Breaking down starch into maltose and glucose is an important problem to be solved simply due to the usefulness of both of these saccharides. Maltose is used as a sugar in bread production. As other sugars do, it feeds the yeast in helping the bread to rise. It is also used in the production of beer and is used to extend the shelf life of certain food products. However, as it is only 30% as sweet as ordinary sugar, it is not used as a sweetener and does not have any other uses. Glucose is one of the most important ingredients of the food industry. It is used as a sweetener in multiple food products such as sweets, bakery products, and ice cream. It is also used in the production of processed food. So, how is this process done outside of the human body? First, starch granules are mixed in water with the ratio of 35% starch and 65% water. Starch, due to its large size, does not dissolve in water. This is where the starch is gelatinized. The process of gelatinization heats up the starch granules until they begin to absorb the moisture. The granules start swelling and eventually burst to reach starch molecules into the water. This is an irreversible process of dissolving starch in water. After gelatinization, the gelatinized starch goes through the process of liquefaction. It is heated to a temperature of 95 degrees Celsius for 2 hours. This causes the gelatinized starch to become a mash of starch. This mass of starch consists of 0.3% of glucose, 2% of maltose, and 97.7% of oligosaccharides. Oligosaccharides are simply molecules made up of a low number of saccharides. They are made up of more than two molecules of glucose, obviously, as two or less molecules of glucose would simply be maltose or glucose itself. The final process is saccharification itself. Depending on the preferred product, from this process, the process can be changed. If the mash of starch is mixed with amylase and heated at 60 degrees Celsius for 72 hours in an environment of pH 4.5, the main product will be 97% glucose, along with 1.5% maltose derivatives and 1% of other oligosaccharides. If the mash of starch is mixed with amylase and heated at 55 degrees Celsius for 48 hours in an environment of pH 5.5, the main product will be 84% derivatives of maltose, 12% other oligosaccharides, and 4% glucose. The reason that starch has to go through gelatinization and liquefaction before reaching this process is to increase the surface area of the starch so that the process of enzymatically breaking down the starch is quicker. The larger surface area allows a larger volume of substrate, in this case starch, to come in contact with the enzymes, in this case amylase, active site. That's not where it ends though. When science solves a problem, there are usually extraneous impacts of that science, both positive and negative. In fact, using enzymes is a profitable way of producing glucose and maltose. In fact, the process of using enzymes in food production is expected to reach $2.3 billion by 2018. This significant expansion of the enzymatic market has led to an increased number of students enrolling themselves in biology courses such as molecular biology. With a rapidly expanding industry, enzymes have an extremely large economic impact in the food and education industry. In fact, the educational impact is part of an increasing social and cultural change. Traditionally, people of conservative cultures do not tend to venture into different courses where they believe success is not possible in regards to education. These expanding industries inspire belief into people that success is possible in almost any industry they venture into. However, what makes this industry possible, the enzymes themselves, may be a reason for many to dislike products produced by or synthesized by enzymes. Particular enzymes raise ethical and moral concerns over their manner of production. For example, rennet is an enzyme produced in the abomasum, the fourth stomach chamber of calves. To extract this enzyme, calves are butchered and sliced into small pieces. This especially raises concerns in the vegan and the vegetarian population. However, unknowing people can be led to believe that all enzymes are produced this way, which they are not. Amylase, used in starch saccharification, is in fact only produced from the bacterium Bacillus. Improper use of enzymatic preparations can have legal and political consequences, as well as invoking the hatred of humanity by the butchering of livestock. The Federal Food, Drug, and Cosmetic Act of U.S. Food and Drug Administration states that there are 5 constitutional requirements for any food additive enzymes. These requirements are the identity of the additive, the use of the additive, the intended effect of the additive, an analysis of the additive in food, and full reports of safety investigations regarding the additive. Enzymes have far-reaching impacts beyond the common industry such as the economy. Regarding the butchering of livestock, enzymes are not as environmentally detrimental as some seem to be. Industrial biotechnology, such as the production of enzymes from bacteria and fungi, help overcome these ethical concerns. Industrial biotechnology also significantly increases the eco-friendliness of enzymes. A study comparing the enzymatic process of degumming soybean oils and the burning process of degumming soybean oils showed that the enzymatic process produced 44 tons less of greenhouse gas per 1,000 tons of oil produced. A literature environmental assessment of enzymes in industrial production shows that industrial enzymatic processing and synthesizing allows movement towards cleaner production in industries. These enzymatic processes also reduce the use of energy, chemicals, water, and raw materials such as food. In the end, it is up to the end user to make the decision regarding whether or not the positives of using enzymes outweighs the negatives.